So we can start. I will leave the door open in case more people come. I want to introduce Olivier Verhamme to you. He's a finishing PhD student at KU Leuven, working on massive stars, but he worked once on low mass stars, I still remember. So he is visiting us after a run in La Palma. And yeah, I'll give you the floor.
Thank you. So yeah, I'm Olivier Verhamme. I'm indeed part of the KU Leuven. I work with, at the moment, with the group of with Jon Olaf Sundqvist, but co-supervisors Uxan and Alex de Cotter, and there's a lot of people here as well that I work with on a semi-regular basis. And I thank the AAC for allowing me to speak here. Thank you very much. And I'll be talking about empirical mass loss rates and clumping behavior of B supergiants obtained spectroscopically. This works. Okay, quick overview. I'll be talking about massive stars, why we care about massive stars, why we care about their winds specifically, then how to fit big parameter spaces, because that I'll get into. These winds are sometimes very hard to model if you want to get into the details of the winds at least. And then how we can see the clumpiness, the complicated behavior of these winds observationally. And then also how the empirical derived mass loss rates compare to actual models, what we use right now and stuff like evolutionary codes, and what the consequences are of the disagreement or the apparent disagreement between the observationally and theoretically derived mass loss rates. So first off, massive stars. Massive stars are relatively uncommon compared to their low mass counterpart. We define or try to define massive stars as everything higher than 8 initial solar masses. You could go a bit higher, could go a bit lower, but the idea is that they are massive enough that when they go through their evolution, they create heavy enough elements in their core that at the end, if they go at supernova, they turn into one of these more exotic objects like a neutron star, black hole. The stars I'll be talking about are even more than this. Usually they are 10, 20, 30 initial solar masses. So it's even higher than this. And even though they're a lot less common than their low mass counterpart, who have, to be honest, a pretty similar lifetime in the sense that they just expand, 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 and then at the end they go something drastic and turn into some compact thing in the end. The reason we care about them is because they have a big effect on the region they're in. They have very strong UV radiation, so they reionize the environment they're in because they're so hot. And their winds and also their supernova are very good at enhancing the region they're in chemically. So they make these heavier elements in their core, and then through their winds and through their supernova, they expel this back out into the environment. So they're important to for the metallicity evolution of the environment they're in as well. Now, mass loss in different stars. Well, every star pretty much has some sort of mass loss. Even the sun or solar-like stars, when they're in their main sequence, these low mass stars have some sort of wind. There's our gas pressure winds. So basically the outer layers of the star are hot enough that a certain part of the wind of the elements there, or the particles there, move fast enough that they exceed local escape speed and they escape out. And this results in a very low mass loss, so 10 to the minus 14, I think, is for something like the sun, but pretty relatively fast, let's say, like a couple 100 kilometers a second is then the local escape speed, so they are relatively fast. On the other hand, if you take the same star and just evolve it, or a bit heavier maybe and evolve it, you end at some point in an AGB star, which has very big winds, but they're produced completely different. Here you have an evolved star with a very loosely bound envelope, and this loosely bound envelope gets pushed outward by some pulsation, gets a bit further out. There it becomes cool enough that it creates stuff like molecules, dust, and then the radiation pressure from the central star gives it the last push to really become a wind. And this creates low velocity winds, so tens of kilometers a second, but pretty high mass loss rate. We're talking 10 to the minus 7, 10 to the minus 5, something like this solar masses a year, which is really high. And then we go to the massive stars, and these winds are completely different. They're also radiation-driven winds, so it's also the luminosity, the radiation of the central star that is pushing against the material, but instead of pushing against dust, instead of pushing against some object, it actually transfers its momentum through the line transitions. So you have your atom, it has line transitions, and when correct wavelength of light comes near it, it absorbs it, and the electron gets to a higher energy level, but the momentum gets carried in the atom and it gets a bit of momentum forward. Now, when it gets this little momentum forward, it is actually a little bit blue shifted, and that allows it to absorb a new wavelength, a new energy of wavelength on the same line transition. Here I made like a hydrogen atom because it's the easiest. It absorbs this new wavelength quite efficiently. It pushes itself out of the shadow of wavelength it just made, and then it gets even more momentum, and then it's blue shifted even more, and then it gets even more momentum. Now I produce here a hydrogen atom. In reality, the efficient atoms to do this with are the ones with a lot of line transitions, because as they are actually pushing against the line transition, the light is really being caught by the line transitions. The more line transitions you have, like in iron, the more efficient you are at catching this radiation getting pushed forward. So this is the basic idea of why these massive stars with very high luminosities have these very fast winds for thousands of kilometers a second with up to a very high mass loss, up to 10 to the minus 4, 10 to the minus 7. 10 to the minus 4 is a bit extreme, maybe. These are more Wolf-Rayet-like stars, but 10 to the minus 7, 10 to the minus 6, certainly for the B-supergiants we'll be talking about now. Yes, there we go. So this is the base idea of why these stars have winds, but why they are clumpy is slightly more complicated. There's two main reasons why you expect them not to have a smooth outflow. The first one is that the region that the wind is launched from is actually not smooth either. If you look at 2D, 3D simulations of O and B type stars, you see that the layer where the wind actually gets launched is very turbulent. This is due to the very high luminosities. Locally, you can induce Eddington factors that are higher than 1, and then you create a lot of turbulence in the star, which actually creates that very turbulent area where the wind eventually gets launched from, and therefore you get this clumpiness, this inhomogeneity gets carried on into the wind. This causes some inhomogeneity, but not the main one people think of when they think of inhomogeneity in massive stars, specifically in radiation-driven winds, is the line deshadowing instability, which is more of a theoretical thing where if you have an atom, so like I said before, you have this atom, it carries the wavelength and it gets the light and it gets pushed forward a bit. Now imagine it's not just one atom, but obviously there is like stuff in front of it, closer to the star, stuff farther ahead. In the ideal case, everything would be moving at its correct velocity, that it still has some new light to absorb. But imagine now that you have one atom that for some reason is moving slightly slower than it should be at its radius. Now, suddenly, the light it's supposed to catch is being absorbed by the material slightly closer to the star that is moving at its correct velocity. So there's no new light, or not the correct light, is coming to this line anymore, to this material. So suddenly, it's losing a part of its acceleration, which means it is slowing down compared to its neighborhood, which means it's even more material in front of it is catching the light it should supposed to be catching. So it falls back sort of into the material coming on it. And this causes a very clumped behavior because this is a runaway effect. Once it starts slowing down a bit, it loses its acceleration mechanism, which makes it slow down even more. It makes it slow down even more. And it causes this very clumped behavior that you can see here, which is a simulation from Florian Driessen, where he, for different metallicities, shows this clumping behavior. And this is a very, very, very clumped material. So clumped that from this, people assume that everything in between the clumps is so void of material, so empty, that it's not even worth modeling them, or not modeling them in detail, at least. Okay, so this is what the winds look like, but all this theoretical or all these massive star winds, why do we care? What is the main reason for wanting to study these massive star winds, even at their main sequence? Is because at these very high masses, stars tend to lose a lot of mass this way, and this influences their evolution quite significantly. What we did here is, or what Robin Björklund in 2022 did here, is he took two 60 solar mass stars and made them two MESA models out of them, like this, but all he changed between the two is the mass loss prescription. The mass loss prescription in codes like MESA and GENEC, how they work is they just take in some key parameters from the star, let's say mass, luminosity, temperature are the main ones, metallicity is obviously also there usually, and then it just spits out the mass loss rate. So let's say you take the star here, there's a certain temperature, a certain luminosity, a certain mass that is being produced by GENEC or MESA, and then you just get the mass loss rate out. And the reason we do this in a quote-unquote simplified way is because we want to make sure that our MESA models or GENEC models don't take forever to run. So this is actually a smart way of making sure that the computation time stays down. And these prescriptions are usually based on models, theoretical models, people who run 1D stellar structure and wind models. And they just looked at what the logical mass loss rates were that they got out when they ran these self-consistent models. And then they get some sort of fit procedure through them to get a simple function out of it, and then you get a mass loss rate prescription. But when you change them, when you go from the standard Vink one, which is the one you use in MESA, GENEC, and so on, and you change it to the Björklund prescription, which is a slightly lower mass loss rate prescription, you can see that the star evolves very differently. Even up into the main sequence, you see that you get two relatively different stars. Then after that, they become significantly different. And at the end of hydrogen burning, the Vink rates give you what is probably a classical Wolf-Rayet star. It has lost its envelope. It is at the correct spot, more or less, for Wolf-Rayet star. It's 22 solar masses. If you use the reduced mass loss rate from Björklund rates, you get something that is not even resembling a Wolf-Rayet star. It's 47 solar masses. And stuff like this matters if you want to know about how these Wolf-Rayet stars, but also masses of black holes actually get formed. Because if you use the Björklund rates, it becomes very, very hard to actually produce these Wolf-Rayet stars singly, at least. You need something to strip the envelope away. This can be binaries or something else, but it can't just be a single star. It becomes super, super hard to do so. And also, exactly as I said before, if you want to know what masses of your black hole progenitors are exactly, if you want to know why the stellar mass black holes are the way they are from gravitational waves, it's also important that you know how they evolve to get there, what the initial mass of that star is, if you're interested in that. So what is the detailed difference between these two prescriptions? Well, I've plotted here the Vink prescription over temperature. Like I said before, it's not only temperature dependent. There's luminosity and mass in there as well. But this is it over temperature. And this is the Björklund rates over temperature as well. And then we have another one, the Kritichka rates, which are relatively similar here as well. The big difference, as you can see, is this jump upwards between the red one and the black one, where the red one has something called the bistability jump. And the bistability jump is the enhancement of mass loss rate around 25-ish kilokelvin, depends a bit on the star, because iron 4 recombines into iron 3. So if around where the wind is launched, because like I said before, the thing that's actually pushing the wind are these line transitions. So if you recombine iron 4 into iron 3, you add a bunch of extra line transitions. This could make the wind more efficient, and this could result in this jump upwards. And this is what they saw in their models. Now, more recent modeling from Björklund and Kritichka, who do globally, or not globally, locally consistent, hydrodynamically consistent models, they do not see this jump upward at all. Even though they do see this recombination of iron 4 into iron 3, they do not see this jump upward at all. So what I'm trying to do is figure out, with the help of spectroscopy, if this jump is real or not. As you can see here, the jump that we're trying to figure out, if it's here or here, is quite big. We're looking at an 1.5 magnitude difference in this specific plot. So it should be relatively easy to find, and I'm not the first person to try and do so. We have Markova and Puls from 2008, we have Rebellius from 2021, we have the Burgers from 2024, all actually looking at the similar problem, all looking if this jump is here or not, if this supposed bistability jump can be observed observationally, and all of them found that it wasn't there, that they found no real evidence for the jump being present. So that means that observationally, it's very hard to show that this jump is here. What I'm trying to add on it is that, okay, these models, they all showed that there wasn't there, but they had to either assume a clumping factor or assume a smooth wind, assume the clumpiness of the wind, because they were limited by only having optical data or only having certain continuum data. But if you have access to UV data, which I have thanks to the ULLYSES collaboration, you can actually get the clumpiness of the wind out as well. And this is, I'm going to try and show you why. So if you only have optical data, the main thing you look at when trying to figure out the mass loss rate is the H-alpha line. H-alpha line is very, very sensitive to mass loss rate, and mostly the peak of the H-alpha line is very, very sensitive to mass loss rate. So what I show you here is one model of a star and two lines that model produces, with a clumping factor of 40 and a mass loss rate of 8 times 10 to minus 8 solar masses a year. Clumping factor is defined as the density squared average over the density averaged squared, which means that it shows you how much overdense the overdense regions are. So a clumping factor of 40 means that the dense regions are 40 times more dense, more or less. It's a bit more complicated than that, but more or less it shows you how much overdense the overdense regions are. Now, if you only have optical, you only have this H-alpha line, and you change the clumping factor to 1, but then increase the mass loss rate to be 5.1 times 10 to the minus 7 solar masses a year, meaning that the square root of the clumping factor times the mass loss rate stays similar, you get an H-alpha line out where the peak is more or less at the same spot. If I would simplify the models we use, and if I would fine-tune them a bit, you could get the exact same line out. In optically thin clumping, as we call it, in a specific way of handling the clumping, this square root of the clumping factor times mass loss rate would always produce the exact same H-alpha line. Because we use a bit more complicated clumping parameters here, it's not the exact same because the onset of clumping and so on influences the H-alpha line as well. There's a lot of things going into the H-alpha line here. But what matters in the end is that it's very hard to distinguish clumping factor and mass loss rate if you only have optical data. So the way to solve this is by also looking at UV data, which behaves, or UV resonance lines, which behaves differently to this clumping factor because they're a different type of line. The H-alpha line is a recombination line. The silicon, this UV resonance line is a resonance line. So they behave differently to the clumping factor. That means that if you have access to the UV data as well, you can clearly see that this line is not the same. And you can disentangle or break the degeneracy between the clumping factor and the mass loss rate. And that's the main goal of what I'm going to try and do. Now, I talked a lot about the clumping factor already, but all this clumpiness behavior, all this clumping is actually a very 3D type of behavior. It's a multi-D behavior that you don't get out of 1D models by itself. You need to add them afterwards. So why not just use 3D models instead of 1D models to fit the actual lines? Well, that's because the 3D models we're working with right now, the radiation hydrodynamical models right now, take on the order of weeks to actually get one model out. Now, if you would know for sure that you got the correct guess on guess one for your star, this would be somewhat okay. But because you usually need a bunch of models to actually check which model agrees with the spectra, this becomes very, very hard. Also, because after these weeks, you don't have spectra yet. Actually creating spectra from your 3D hydrodynamical simulations is not super straightforward. There's a lot of work there as well, which we're working on right now in the Team Yun group there, but we're not entirely done with that yet. So for now, until we get better computation time or more efficient computation time and better spectra, we need to add these parameters that we see in the 3D simulations into 1D simulations somehow. And we do that in FastWin by adding these three parameters. The clumping parameter, which I already talked about, showing you how dense the dense regions are compared to the average. Then the interclump density, which tells you how dense the non-dense regions are compared to the average. Let's say if it's 0.5, that means that everything in between the overdense regions is at 50% of the average. And then you have something more complicated. It's called the velocity filling factor. And this tells you that if you have your clumps now moving, they're not everywhere anymore, right? They're localized in specific spots, which means they're also localized in velocity. And the velocity filling factor tells you how much of the velocity space your clumps are actually filling. And this is important because if they are very non-filling, let's say they're very concentrated on one area in velocity, that's allowed a lot of light at specific wavelengths to pass through and not really interact with the clumps because these clumps are only at a specific velocity. And because of the blue shift, they will only interact with a certain specific wavelength of light. And that's what I'm trying to show here. The effects of velocity filling factor on the actual lines. So these are UV resonance lines I'm showing here. They're very wind sensitive. What I'm showing here is that if you take a specific mass loss rate, specific everything else, but just change the velocity filling factor, you get slightly different lines out. And the idea is that once you decrease the velocity filling factor to something below 1, it's impossible, more or less, to fill for the lines to be ever fully saturated. Here it's only a very small effect, and that's because I put the interclump density at 0.3, I think. But once you put the velocity, the interclump density, sorry, at low enough values that the regions in between the clumps aren't too dense, you actually see the effect quite clearly that once you induce some velocity filling factor that's not 1, here it's 0.25, you see a clear effect that the troughs, the absorption can never be fully saturated because there's always some light leakage going through. Now this effect is, to be fair, once you get to slightly higher values of interclump factor, pretty minor. Then the effects of interclump density are, well, for one, that if you have a velocity filling factor that is not equal to 1, it allows you to still get a saturated line or more or less saturated line, but also increases the effective opacity. So in how it is coded is that if you increase the interclump factor, it increases the effective opacity by a slight bit every time you increase it. So that's what you can see here, and here the line just gets slightly stronger if you increase the interclump density. With the clumping factor itself, I don't show it here again, but I showed it before. There's a major effect on H-alpha. You can, if you increase it, your H-alpha line, all your wind lines will just become a lot stronger because there is more material there, basically. I talked about quite a lot of parameters so far, but the whole slew of parameters we want to get out of these spectra is 7 Seller parameters: effective temperature, because we want to know where in the bistability geom they're actually located, the log G, so the surface gravity, the helium abundance, because we needed to get accurate temperatures out as well, CNO abundances, and then the max V sun I. So this is the rotational speed. This is not really the rotational speed, it's the rotational speed and the macroturbulence together. We don't fit macroturbulence separately. We all put it in one broadening mechanism, which we call max V sun I. So this is rotation and macroturbulence together. And then we have 9 wind parameters, which is mass loss, obviously, and then velocity, so V infinity, which is thermal wind speed, the speed of the velocity of the wind when we look at very, very far away. Then we have the clumping factor, interclump factor, or the interclump density, and the velocity filling factor, which I explained before. Then the clump start, which is where the clumping actually starts, because it can't start at the actual atmosphere. It starts out in the wind, so you need to define where it exactly starts. You need to define where it reaches its quote-unquote full value, how it increases as well. And then you have beta, which is how fast the wind accelerates. And then you have wind turbulence finally. And then you have 2 X-ray parameters, because in these stars, you have material moving. And once 2 clumps kind of hit each other, because one is moving faster than the other, they hit each other. This can cause them to heat up. And this can cause X-rays. And what Fx is the X-ray filling factor. So the amount of material that is producing X-rays, and then U infinity tells you what the difference of the speed was between these two clumps hitting each other. And this is our 18 parameters, and this is a lot of parameters to fit at once. So how we do this? Well, naively, there's a couple ways to fit anything. You can show how 18 parameterized loss function looks like if you would plot it as an 18-dimensional cube, so to say, and see how the loss function changes over time. You can indicate this as the height sort of the mountain. With the higher the mountain, the lower the loss function. So you want to get on top of the mountain somehow. The most straightforward way to fit anything, for in recent times at least, is to do something called gradient descent, or here gradient ascent, I guess, because I flipped the loss function towards up instead of down. What you do there is you take a random guess. You look at where you are right there, and you look at what the gradient is of where you are there. And then you just follow that gradient for a certain step size, and you do it again and again and again until you reach somewhere where it's flat. And you assume that this is the global minimum. If you have very few parameters, or you know very well where the initial guess should be, this can work really, really well, because it's super efficient, time efficient, because you don't need many models to be computed, and it's very fast. And if you know where the global minima is, more or less, you're sure you're going to be at the global minima. The problem is, if you don't know for sure where the global minima is, or you have so many parameters that you know it for some parameters, but definitely not all, this becomes hard, because it will just stop once it finds a flat spot, once it finds the top of a hill. But it could be that over here is another even higher hill that it just never really got to, it never explored. A way around this is by using an MCMC fit of Monte Carlo Markov chain method, where you, instead of putting one guy out there, you put this ton. So you take all his friends and just throw them over the entire mountain range and just put them somewhere randomly. They compute what the loss function is where they are right then, and then they just move a random position. So just like take a step in a direction. And then they recompute what the loss function is right there. And if it's better than it was before, they stay put. If it's worse than it was before, they go back. Now, because the step is random and you can change the step size randomly as well, the advantage of this is that you usually get out of these local minima, or you don't get stuck in local minima as much. You're still not sure that you're at the global minima because you never compute the entire parameter range. You usually do a big part of it, but not the entire thing. So there could be a combination of parameters that is actually lower that you never checked, but you're more certain that you checked enough of it that you'll get close to it at least. The disadvantage is that if you have somebody over here that's just running somewhere is clearly not a good place, it will take a long, long time for it to actually compute meaningful models. It will take a long time for it to actually get somewhere where it's adding to the useful models, to the models where you actually want to compute stuff like uncertainties. So you waste a lot of models, and that's something we want to avoid because our models are relatively fast, but not instant either. So what we do instead is we do something called a genetic algorithm, which starts pretty much the exact same way as an MCMC. You just throw a bunch of people out there and you just check what the loss function is at that position. But instead of making them just walk randomly based on the information they know and only them, you make them interact. So you make them say, okay, get together and figure out who is clearly in an awful position that you don't want to be. Somewhere way down there where it's just clearly that's going to take a long, long time for you to reach any values that are close to the value we're looking for, any values that are close to a low enough chi-square, whatever you want that to be. So then you just take them and you move them to positions where you know that reasonable chi-squared values have been found. So you move them to one of the positions of the good ones, quote unquote, where it is already known that the chi-squared isn't awful, at least. And then you make them move around randomly again. The step size, again, can be as big or as small as you want, so you get out of your local minima. And this way, you hopefully avoid computing too many, quote unquote, useless models. So you immediately get into a more efficient chain where you always get reasonable models out, at least fairly quickly, only after a couple of, quote unquote, steps. Now, the name genetic algorithm kind of tells you already that this is usually not referred to in a way that is people walking on a hilltop, but it's based on evolution. So how they usually talk about it is that your first step or your first guess is the first generation. And then after you compute the fitness of that generation, the loss function, whatever you want it to be, you reproduce. So you take some of the good models and you mix the values randomly, however you want them to mix, and then you make a mutate. So these random steps now are called mutations, but it's the exact same idea. The GA, or the genetic algorithm I use, is called Kiwiga. It's been produced by Sarah Brands, and there's a paper in 2022 where it is explained how it works. And the synthetic spectra they use, or the synthetic synthesis code they use, is fast-wind, as I mentioned before, to actually compute these models to compare to the observations. Now, there are a couple of GAs that are very, very similar out there. I know that there's a paper by Hawcroft 2023 or 2021, I don't know for sure, that uses a GA that is differently named, but pretty much the exact same GA method, at least. Okay, so now the GA and numbers, how many models do you actually need to compute? Well, for one star and for one B-supergiant spectra to be fitted decently, we need about 50 to 70 generations, depending on the star. Because there's 100 models in each generation, that means we need about 6,000-ish models to be computed. And that shows immediately why we can't do this with 3D models, even though they would reduce the parameter space probably a bit if you use 3D models. You would still need thousands of models to be computed if you want 3D models. If all of them take weeks over 48-ish cores, then you would be computing forever. This would never end, pretty much. But if you use fast-wind, which only takes about 45 minutes, you're done in 190 days. But luckily, you're not really done in 190 days. That would be ridiculous. What you do is, because they don't need to interact when they're actually computing the models themselves are all separate. The only time they need to interact is figuring out which parameters they want. You can just spread them over 107 cores, and then it takes about 2 days to compute the full fit. You get something out in 2 days, which is reasonable. And the main advantage you have here, compared to some other method, is that at the end, you end up with global fits and global errors. What does this mean? This means that because we computed all these different combinations of parameters and not just the ones that were at the end when we want to make a grid out of it, for instance, we computed all these different combination of parameters around the good fitting space. All these degeneracies between clumping factor, mass loss rate, interclump density are already taken into account in the errors. So all the errors are global errors in the sense that the error on the mass loss rate is already taken into account all the other degeneracies with mass loss rate that are there. And there's quite a couple. So yeah, this is very useful. The reason we use fast-wind and not something like CMF-gen or power is, one, because the clumping behavior in fast-wind is more evolved or more well-produced. Stuff like interclump density and stuff is not present in CMF-gen and power. I think maybe there's some version out there, but they also take a bit longer. According to the people who actually use this, it takes about 10 hours to run one model, and then suddenly this 2 days becomes a lot longer because your 45-minute becomes 10 hours, and then we're looking again at the computation time issue. Okay. So this is what a regular output of Kiwiga or a GA looks like. So what you have here is the fitness function, so 1 over the fitness function. So we're again looking at a peak instead of a trough. And here is a parameter. Here I chose mass loss rate because that's the one we're usually focusing on. But we also have one for temperature, one for clumping factor, one for all of the 18 parameters we have here. And the color shows you which generation this model was a part of. So if it was generation 0, it will be the bluest. If it was the latest generation or last generation 63, it will be the greenest. The red line shows you where the best fit was, and the grayish region shows you the 1 sigma, and then the lighter gray shows you 2 sigma. And this is based on a statistical approach called RMSCA, which you can read about in a couple papers, one of them being Verhamme 2024. Now, so this is regularly what the peak looks like. You can determine your mass loss rate and the errors on it. And you obviously also get your fits of your actual lines out. So here's a selection of lines we fit. And this is randomly chosen, so some of them aren't perfect. But overall, the fit quality we get out is decent. And because all of this is taken into account, the worse the fit is, the bigger the error margins will be with the method we use. So if you see something like this, you can be sure that the error margins we get out are going to be quite a lot bigger. Okay, so now let's look at the actual results. So I have a sample, thanks to, again, ULLYSES and Xshoot-u collaboration, of about 40-ish stars in the SMC and LMC, for which we have UV and optical data. And here they are on the HRD. The stars are the LMC and the spheres are the SMC. Later on, I'll sometimes use cubes to represent the SMC, but the LMC are always the stars. And the color here shows the mass. These evolutionary tracks are just missed evolutionary tracks, so they are not tailored to these type of stars necessarily, but they show you some indication of where you expect them to be evolutionary. They're somewhere right after the main sequence, somewhere in this HR gap. Our masses also range quite highly. Okay, so I'm going to show for most of parameters, both SMC and LMC. One caveat on this is the thermal wind speed, for which I show only LMC. This is because we're still in the middle of doing the SMC analysis, so there's some things to still be worked on. So always when I show SMC and LMC, the LMC we're quite certain we looked at, there's no problems anymore. SMC is still some work here and there, some values might change, but the main idea is probably still there. So what we show here is thermal wind speed over effective temperature. Effective temperature in my plots will, I think, almost always be decreasing, so from hot to cool. This is to keep in line with the typical bistability plots that also always use this hot to cool. And the color in a lot of these plots will be the Eddington parameter. This shows you what the radiation acceleration over the gravitation acceleration is. So in other words, how hard the luminosity is pushing compared to the mass is pulling to whatever the star is throwing out there. Okay, so what you see here is that the thermal wind speed with the effective temperature is extremely linear, except for these two. They are extremely linear, and this is also something that's been found in the work by Callum Hawcroft in 2023, who looked at a pretty big sample, but focusing only on thermal wind speeds. He found this behavior as well, and we find a very similar behavior. Now, why we don't find that behavior for these two, or at least like huge error margins for these two, is because at these low temperatures, the mass loss rate becomes low enough that the features we use to determine thermal wind speed become very, well, they kind of disappear. The lines we use that are normally wind lines, the winds become so weak that they kind of become atmospheric lines again, and you just lose that information. So that means that these two don't really have a determined thermal wind speed, at least not from the analysis we did here. Okay, then we go to the clumping factor, for which we have SMC and LMC results. The problem here is that we don't really have a nice behavior. I showed here over temperature again, but we tried stuff like mass loss rate, the beta parameter, all the other logical wind parameters, and see if there is any correlation there. And most of them show scatter and relatively big error margins. They're not immense, but they're relatively big. There is some, if you want to see it, here some trends from the B stars on, but it is tenuous, huge error margins. I wouldn't take this as like, oh, there's a clear trend here or anything. And the SMC even more so. This is just a bunch of values scattered around. There's no real trend here to be found, sadly. Now, something interesting is that from the LDI simulations, the LDI I explained before with the reason we have these expect very clumped behavior out in the wind. From 2019, we expect the O stars to have a higher clumping factor than the B stars. This is from hydrodynamical simulations. And what we see is that this might be true because three are technically O stars. They used to be classified as B stars, but then new data came out and they became O stars all of a sudden. But they're hot enough to be O stars for sure. And yeah, they're higher than the beginning of the B stars, but again, higher margins. Not really sure if that's true. And in the SMC, we don't really have any O stars to compare the B stars to. So, okay, then intercom density, even though we're at the same struggle again with large scatter, large uncertainties for the intercom density, even more so, it is actually slightly more to say here than for the clumping factor because of the fact that if we just average them out, if we just take a weighted average of these points, assume that the error margins are correct, which if our method worked correctly, they should be somewhat. We get a value of on average from 0.38 plus minus 0.23 when just taking into account the LMC. Again, for the SMC, there's some work to be done, so we haven't included them yet in this average, but it won't be very different from the first test cited. And this is surprising because, as I said in the beginning, from LDI simulations, we expected that this interclump density was very, very low close to 0. We're talking about people expecting it to be 1% at the highest 10%, and we find it to be 40%, which means that 40% of the wind mass is in the interclump according to this LMC sample. Again, high scatter, but still, it doesn't go towards very low values. It seems to go toward pretty high values. And this is interesting because a lot of codes like Power, like CMFGen, don't even include them, or irregularly don't include them in their analysis at all, and just assume it to be void. FastWind does include it, but the way it includes this is because it assumed it to be very low. They do a two-component medium where you have the interclump density and the clumping factor, all clumping material all the way on the other hand in the density scale, which means that this is very different from what we actually see, because what we more see is something like we see in the 2D RHD simulations, which do not take into account LDI, but do take into account this turbulent launching region, or it's just naturally there, I should say, where if you look at this plot, it shows you the probability of finding a density in the wind at a certain value. So at the 0 is the average. So if the chance of you finding, if you take a random density cube or a random cube in a simulation, find it at density average, finding it above average, and finding it below average. And it turns out that if you convert this result from the 2D simulations to something akin to interclump density, you also get around this 40% out, which is interesting, and it's maybe a bit of happenstance that this turns out to be the exact same, but it's still interesting nonetheless, and it shows that we should probably rethink the way we're doing this interclump density entirely. Pay a lot more attention to it and not just focus on the densest parts of the winds, because the interclump is already significant. Then the most important bit is the mass loss rate. That's why we started this whole thing. So here I show again mass loss rate, effective temperature, gamma E's. For the LMC, you see that it decreases nicely with temperature. And then you have some on the lower end, which are all to do with the fact that gamma E becomes low. So there's little luminosity for a lot of mass. There's a lot of pulling, not a lot of pushing, which explains why these would have lower mass loss rates. And you sort of see a similar thing for the SMC. The problem, if you want to compare this to the prescriptions, is that in the prescriptions, stuff like mass and luminosity can be kept nicely the same. If you want to see the trend in temperature, they just fix the mass and luminosity. In real life, when you're looking at a real star, you don't have the luxury of fixing the luminosity and the mass of your star. You're looking at real stars, they have all different masses, all different luminosities. How do you deal with this? Well, you can just take these masses and luminosities you figured out from your stars and put them in the actual prescriptions. And then the prescriptions give you a mass loss out, and you divide that by the found mass loss. And now you have a clean way of comparing what the observed values are compared to the prescription values. So that means that if it's at 0, because it's a log space, that if it's at 0, that means that the prescription and the empirical values agree perfectly. If it's above 0, it's overestimating. So if it's at 1, it's 10 times overestimating. If it's 2, it's 100 times overestimating. Same for LMC and SMC. And if it's below, obviously, it's 10 times underestimating, 100 times underestimating. What you see in the LMC quite clearly is that up until a certain temperature of like 23,000 Kelvin, all prescriptions, so all 3 prescriptions I showed in the beginning, including the Vink one, all seem to agree relatively well. They either overestimate in the Vink case by a factor 2 or underestimate in the Kritichka or Björklund case by a factor 2. But they are all within a factor 2 on average, at least. So that's fine. That's like acceptable. The problem is once we get to the biostability jump, the Vink rates, of course, shoot up, as I showed before, and they start overestimating on average by a factor of 40, but up to a factor 100, which means that if you're running your MESA model and haven't really looked at what mass loss rate scheme you're using because you haven't thought about it or you just don't really care about mass loss rate that much, then you might be overestimating the mass loss rate by up to a factor 100, which is huge, right? Because this, if your star has a specific temperature, this could happen during your main sequence, which means for a very, very long time, which means you get out a very, very different star in the end, as we showed before. For the Kritichka and Björklund rates, they seem to agree relatively well. The Björklund rates stay underestimating by about a factor 2 on average, while the Kritichka rates have like a localized above and below. So both of them seem to be behaving relatively well. If you compute the offset, it's still about a factor 2 for both of them. And then you have this one, which is underestimating by quite a bit for the Björklund rates, and the other ones seem to agree. If this is an outcast or just an indication of the Björklund rates decreasing too quickly for low temperatures, we can actually look at the SMC to see if that's the case. In the SMC, you see a very similar behavior. It's a larger scatter, which could be due to the fact that some of these mass loss rates might still change a bit, but the similar behavior is still there, where once you hit the biostability jump, suddenly the Vink mass loss rates shoot up compared to the actually observed mass loss rates. Again, on average by about a factor 50 to 100, but up to a factor of like close to 1,000 now, which means that the problem might be more severe in the SMC still. What we see on the cool end, actually in the Björklund and Kritička rates is quite interesting. Both of them seem to be decreasing too quickly when we go to the cool end. When we go to the coolest stars in the SMC, they seem to be underestimating the mass, both of them. Now, this bump I showed in the beginning of the Kritička rates, we can't actually probe it because it's at very cool temperatures. This star might be getting close to the bump, but here for sure we're not really estimating the lowest end, this bump that we saw in the Kritička rates. So if it's there or not is still open for debate, but this bump is so small compared to the factor 100 here jump that we see in the Vink rates, that this is like a secondary thing we should look at some point. But when our sample reaches low enough temperatures, then we'll run into other issues like the mass loss rates becoming so low that actually getting the mass loss rates out from spectral will be hard, probably. Now, quickly want to go over some of the effects of changing the mass loss rate for people who are not really interested in the winds themselves, but in stars in general, or in galaxies, the makeup of how these galaxies evolve. There are some studies out there that just played around with the mass loss rate and then did a bunch of different evolutionary models to see what would happen. You have one from Joris Josiek, who changed the Vink rates to the Bestenliner rates, which is an observational scheme for mass loss rate. But most importantly, it doesn't include the jump. And what they saw is, of course, that you, in the end, if you look at the LMC and galactic, get different masses of your stars in the end. You get different end products. But not only that, you get different chemical yields, and the convection zones within the star change over evolution, not only where and when they form, but also how large they are. So that's important. So they're not only changing the end masses of the star, but they're also changing the way the mass behaves, which is quite interesting. And a similar thing has been found in an SMC study where they just played around with changing the mass loss rate by a factor 2 or 6, so still including the bump. So this is very small changes compared to the changes of a factor 100 I think we are probably likely to implement soon. They saw a difference in end products, and again, these changes in surface abundances. So these are relatively small changes, and we still see changes in the actual stars, how they evolve, what they produce. So quick conclusion, I think the mass loss rate prescription we're using right now in stuff like MESA, stuff like GENEC as a baseline at least, is not in line with what we see in observations, at least not in this luminosity and temperature regime. LBVs might be a different case entirely. And a second thing is that from the LMC, at least 40% of the wind seems to be in the interclump region, which means that if we want to improve on how we estimate stuff like interclumping and velocity filling factor, this might be a position or a thing to look at because maybe our description is just off at the moment. And that's part of the reason why maybe we get these large error margins out. Thank you.
Questions? Nothing. I have one actually. Danny, yeah, give me a sec. I'll ask. I have the microphone in the hand. So, the difference between the LMC and the SMC, do you think it's because you still have stuff to do, or do you think it's related to the metallicity? Do you think we reproduce them worse?
So I think the changes that will happen when we look at the SMC further are going to be relatively small. I think at most a factor of 1.5, 2 in the mass loss rate specifically. I don't think we'll see much change there at all. I didn't include it here because we're still ongoing and I'm not 100% sure of it. But one of the weird things I saw so far is that the actual absolute mass loss rate for LMC and SMC, when you do stuff like wind momentum luminosity relation, which should be metallicity dependent to somewhat of a degree as I understand it, is actually extremely similar. They seem to be overlapping, while if we look at the O-star regime, which there's a paper from Bucks coming out or in submission, they saw actually a different trend there. So I'm not 100% sure that's going to keep existing, but it seems like it's there. So the actual changes between SNC and LMC for the B-supergiants are really, really minor, which is surprising because I was expecting metallicity to have a huge effect in the actual mass loss rates. And so far, I'm not seeing that. I'm not 100% confident in it yet, but what I'm seeing right now, it shows that yeah, the metallicity doesn't seem to be changing it heavily at all, which might also be why the prescriptions when compared to the SMC are off more, because they are also expecting this bigger shifts with metallicity. So.
Danny, you can unmute yourself and ask your question if you want.
Hi, Olivier. Danny Lennon here. A very nice work, by the way. So just a quick comment on your last statement that you're expecting bigger dependence of metallicity, mass loss rate on metallicity. Actually, it's not that large when you look at it theoretically, and given the uncertainties in the results, which is why the SMC has been the focus of so much attention in the past. Because when you go from the Milky Way to the SMC, you've got a much bigger gap in metallicity. So I think for the metallicity dependence, you might want to look at Milky Way versus SMC, where your errors don't matter so much. In any case, just a comment and a question on the clumping issue. About 20 years ago, Kari Trundle and I published a few papers showing the bistability jump didn't exist in B-supergiants in the SMC, and that was followed up with a paper of Paul Prather on it didn't exist in the Milky Way B-supergiants either. And at the time, there was a lot of discussion about clumping, whether whether the mass loss rates we're measuring are actually real or not. But the problem is that if you want to solve this with clumping, you need to have much more clumping in the early Bs than in the mid Bs, because you want to decrease those more than you want to decrease the mass rates more than you decrease the mass loss rates in the mid B stars. And your results seem to show, or they do show, that actually the clumping factors don't really depend very much on temperature. I mean, there's a lot of scatter, but they're more or less similar, which is why the result hasn't changed. So my question then is, I mean, to what extent? I mean, what are the observational things which constrain the clumping factors, and how confident are you that you're getting those, you're measuring those correctly?
Yeah. So, so as I understand, the question was, what are the actual observational things I'm measuring to get the clumping factors out?
That's correct.
That's what I tried to show in the beginning a bit, that these changes can be really, really minor. If we go, I actually have the thing here, so I can go back to it. There are some regimes in which the differences can be relatively big, and then we can look at stuff like how the H-alpha mass loss rate predicts it to be compared to the UV resonance trots, and see if we get a difference there for stuff like velocity filling factor, but also how the interclump factor plays around with that as well. It also has an effect on the actual ionization stages, which I didn't really touch upon. But if you change the densities, or how the densities are structured out in the wind, you'll actually get different ionization stages out. So with certain combinations of clumping factor and interclump factor, you will get slightly different ionization stages out. And this is where this restructuring of how we look into the clumping factors will actually have a big effect, because right now, the way it's done in fast wind is that there's only one ionization balance, so to say, ionization stage for each radius, based on an sort of weighted average type thing between the interclump density and the clumping, or the interclump region and the clumping factor, while in reality, because the interclump factor or the interclump density seems to be a bit higher than we expected, we might have to separate them out somehow and do it in a bit more stringent way. So I think we are actually measuring real interclump densities and real velocity filling factors, but because the changes are relatively small, and because our prescription might not be perfect yet, we do get this issue with large uncertainties, and there might be some offset with the actual ones once we get the modeling to be, well, perfect will never be, but like closer to what we think it might be now.
So are you fitting the silicon 4 and the H-alpha lines to constrain the clump? Is that what's driving the clumping, the derivation of the clumping factors?
Yeah, so I think the question was what lines we exactly fit, or?
I guess I'm asking, are you fitting the ultraviolet spectrum?
Yes.
But you're showing theoretical spectra here, right? So I'm wondering what those fits look like in terms of, dependence on the clumping factor.
Yeah, so I don't have them included. I have these plots somewhere, but not in the presentation, but I have one of these plots. So here I can show you that we are indeed fitting these resonance UV lines. This is some of them we fit two more besides these, but here they are. Once they get in lower mass rates, they become a bit messier, but we do fit them. But then if we look at the degeneracies or the interplay between them, I have a plot somewhere. Oh, it's actually right there. Look at that. Where you can see that the degeneracy or the interplay between mass loss rate and clumping factor is definitely still there. I also have some plots now that actually show the interplay between clumping factor and interclump density, which, because they both increase the effective opacity but in slightly different ways, they also have a similar degeneracy where if you increase the one, you can decrease the other and get a decent fit out. But because of the UV resonance lines, even though this degeneracy is still present to some extent because the H-alpha line is still in there and this adds to the total chi squared, the UV resonance lines do allow us to select a region here that is not from like 0 to 50 if we just decrease the mass loss rate enough. There is some estimate on this. And part of the reason why the error margins are relatively big is because the H-alpha line still has this degeneracy, because the other lines have a slightly different degeneracy. It will still, but yeah, we'll still get some link between them out. They're not, even though we are able to constrain the clumping factors, this interplay between them for specific lines is still there. I think that answered it somewhat.
Yeah, I guess basically what this shows is the error bars on the clumping is still very large at the moment.
Yeah, and part of this is definitely due to the fact that they still have this degeneracy there, but we are we are able to break it at least somewhat. We're not completely letting it run free anymore, which is a start.
Oh, it's a great start. Well done.
Anything else in the room? So I guess we can thank the speaker again and go for lunch.
Thanks, Olivier.